We have module 1.4, some chemistry outside of the classroom. And if we look at the Earth's crust, it's mostly composed of oxygen, silicon, aluminum, alkali, and alkaline earth. And we know alkali from the group 1A elements on the periodic table. Alkaline earth, group 2A, the second column from the left on the periodic table. And mostly it's in the form of this silicon dioxide, SiO2. But these aren't pure, as the slide says. You have different forms of these elements that can exist, and they can change. They can chemically change, or they can physically change. And chemical change is something whereby you can change from one form to another, but you can never get its original form back. For instance, lighting a match, an apple that oxidizes. If you let it sit there, you can never get back that original, and we call that a chemical change. Versus physical change here is whereby you can change something, but you can get back its original state, like going from water to ice. You will freeze the water to get ice, and then you can melt the ice to get back the water. So here I'll ask you to pause the video and try these and to identify if something is physical versus chemical. And I'll help you out. Burning a match is chemical because you can never get back that original match. Baking a cake, once you make the cake, you can't get back that original ingredient, so that would be chemical. If you crack a piece of glass and it falls into pieces, you can technically glue it back together, so that would be a physical change. And I'll just touch upon the other ones. Boiling water is physical, rusting is chemical, and oxidation of an apple, that is chemical. Some chemical change here, going from sand to silicon. And what we do here is, this is the making of chips. So what we actually do here is we take silicon dioxide, SiO2, we heat it up to thousands degrees Celsius. And then we heat it up, we add some carbon in there. And what that will do is it will react with the oxygen to make carbon monoxide. So you can separate now the carbon monoxide, and all you're left with is silicon. And depending how well this reaction goes, this will tell you the purity of the silicon. Also going from sand to glass. So here we have a crystalline silicon here, SiO2, which is like quartz. And here it's like a lattice structure. So for silicon dioxide in the quartz, it's very structured for long distances, and they have very distinct melting points. Versus the amorphous silicon dioxide, that's more the glass, where you again you can add additives in there, and that will change the color of the glass. You can have different types of silicon dioxide in amorphous forms, which will give you windows or your cell phone protector case, or sorry, glass layer, bottles. Those are amorphous silicon dioxide, and they have a broad melting point. So what I just mentioned is the process by which you, again, going from sand to glass, you heat up to thousands of degrees, and then you can, when it melts, you can add additives in there to change the color, to change some of its properties. Another thing outside of the classroom is sustainability, which we're all cognizant of. We have here environmental sustainability, where we want to minimize pollution, use up our natural resources efficiently. We have social sustainability, whereby we want to create successful places for the well-being, for our well-being. And we have economic sustainability, where we want to have economic growth without any negative impact on the social or environmental aspects while we're growing economically. Recycling, which is important. We have this cradle-to-cradle recycling, C2C. And what it's telling us is we want to ways to design. We want to find ways to design products where it can be reused and not wasted. So in this case, when we're done with our cell phones, ideally we'd want to disassemble it, melt down and take out the important metals like gold and platinum that's in our cell phone. And then with the other rare metals, we want to be able to reuse it and make new products ideally. However, over 90% of cell phones are sent to landfills and only 3% are recycled. So that's something we want to work on and improve. So here's a chart for C2C recycling. So here if we focus on the inside, we make the cell phone, we use the cell phone, we hopefully want to recycle, and then we extract some of the important pieces of that cell phone or melt it down so that we can reuse to make this recycling loop. And it's important. I mean, the average cell phone contains about 300 milligrams, so thousandth of a gram, as we talked about earlier. 1 milligram is a thousandth of a gram, and it contains 30 milligrams of gold. So recycling is something that we want to be open about in this class. And that concludes our module 1 for now.